Hi, this is Elena Tovar, and today I will be talking about our first lab, which was over constant velocity. So a preview of what is to come is that we found that there was much similarity between the predicted and actual position updates. So here's some physics principles, models, and assumptions that we needed before going into the experiment. So number one, Newton's second law states that the net external force equals the change in momentum of a system divided by the time over which it changes. This is also considered the momentum principle. And we have to assume that there is no force acting on the object if it is moving with a constant velocity. And so here we have a couple of equations that we used in order to update the position. So we use the velocity update formula, which is V final equals V initial plus the net force over mass times the change in time. And then we also use the position update formula, which is final position equals initial position plus the average velocity times the change in time. And so in the velocity update formula, velocity will not change if the net force is 0, which you can see in constant velocity because there's no force acting upon it. So here's a couple of steps that we used to complete the experiment. First, we recorded a video of an object. In our case, we used a marker that was rolling at a constant velocity, which means that it was moving at the same speed and direction. We then used Tracker to track the marker at different frames of time. And then we created a computational model of the predicted positions using GlowScript. And then we used Google Sheets to compare the predicted and observed positions in a graph. So here's a screenshot of Tracker, which is what we used to record the video and update the observed positions. And so on the right, you can see that the graph is already linear, the observed position versus time. And we will later see this in the Google Sheets graph that we created. And then the bottom just shows you each timestamp that we used and the observed positions that we collected. And then the little red diamonds on the screen behind the marker was me going in manually and updating each time frame of where the marker was at that point in time. So then we went into coding. And so we had to update the initial conditions, which was the original position and velocity of the marker. We did this by computing the final velocity minus the initial velocity divided by the change in time. And then we had to update the time and the change in time using what we had in Tracker. We didn't update mass because it doesn't affect velocity. And then we use the position formula to predict the position, and so this can be seen in the while loop that we used in GlowScript. So here's some similarities and differences between data and model predictions. Basically, the graph just shows that it's linear, which means the velocity was constant, and it is in an upward slope, very, very similar, and shows that there wasn't a whole lot of error in our predictions. So some sources of error could have been outside forces such as friction acting on the object because we couldn't really stop this in real time, and then the position tracking, it was kind of difficult to place exactly where it was in each time frame. So here's some questions that we were asked at the end. Number one, what if the positive x and negative x directions were interchanged? Basically, this wouldn't change a whole lot. It would just mean that the slope would be negative rather than positive. And then, is it possible to tell how many forces are being added together to give 0 net force? And this is not entirely possible. In a computational model, you can add that there's no net force acting on the object. So there's no way, but there's no way to prevent this in like a real life scenario. So there's no way to show that there is 0 forces acting on the marker when there always will be. Thank you for watching.